So sound is really just a type of mechanical wave, and it consists of these longitudinal waves which are traveling in a medium, such as a solid, liquid, or a gas. And the properties of these waves determine how we hear the sound. And the human ear can detect waves with frequencies between 20 and 20,000 hertz. This is called the audible range. And sound waves with a frequency higher than this are called ultrasound. And if the sound waves have frequencies lower than this, it's called infrasound. So remember, in a longitudinal wave, the particles are moving back and forth, parallel to the direction of the wave. So you can imagine when the sound is traveling through air, the molecules of the air are moving back and forth, horizontally. And so when the particles are clumped together at the compressions of the longitudinal wave, remember that longitudinal waves have compressions and rarefactions instead of crests and troughs like a transverse wave. So at the compressions, the particles will be clumped together and the pressure will be higher at that point. Whereas at a rarefaction, the pressure will be lower because the particles are all spread apart. So one way to look at a sound wave is by the displacements of the particles, which is the normal way we look at a mechanical wave, but we can also look at it as a wave of pressure variations. As the wave travels, the pressure will vary. At the compressions, the pressure will be higher, and at the rarefactions, the pressures will be lower. So if the sound waves are traveling through air, that means the pressure is fluctuating above and below the atmospheric pressure. And it does so in the same sinusoidal fashion that the particles in the air are undergoing their displacements, which is again how we normally represent the mechanical waves. So to describe the displacements of the particles, we just use the normal equation for a mechanical wave, but we can also find an equation for the pressure fluctuations of these sound waves. So this function tells us how much the pressure differs from the normal pressure. So let's say the atmospheric pressure is 760 millimeters mercury. And so if this function equals 10, positive 10, that means the pressure at this point on the wave will equal 770. If this thing is negative 10, that means the pressure is equal to 750. So this doesn't give you the pressure, it gives you how much the pressure differs from the normal pressure at a point along the sound wave. So in this equation, we have B, which is what's called the bulk modulus of the gas. Now, the bulk modulus is basically something that tells you how hard it is to compress the gas. The larger the value of B, the harder the gas is to compress. And from this equation, we can also see the maximum pressure fluctuation, which is also called the pressure amplitude. And that's going to be when the sine of this whole thing is equal to 1, because the maximum of the sine function is 1. So the pressure amplitude is equal to B, the bulk modulus, times K, the wave number, which remember is 2 pi over the wavelength, times the amplitude. Now this amplitude is the normal amplitude for the displacements of the particles. So you can see that the amplitude of displacement of the particles is related to the pressure amplitude, the maximum value that the pressure can fluctuate around the normal pressure. So again, the properties of the sound waves determine what we hear, what we perceive as the sound. So the loudness of a sound mainly depends on the amplitude of the pressure amplitude of the wave. So, the larger the pressure amplitude, the louder we hear the sound. But it's also dependent on the frequency, because our ears are not equally sensitive to all frequencies. Waves in a certain frequency range will automatically sound louder than waves of other frequencies, even if they have the same pressure amplitude. Now, the pitch of a sound, how high or low it is, depends on the wave's frequency. The higher the frequency of the wave, the higher the pitch of the sound appears. So the difference between music produced by instruments and just regular noise is the frequencies that make up those sounds. So sounds produced by musical instruments consist of the fundamental frequency and the other harmonic frequencies. So when a sound consists of only the fundamental and its overtones, that's what sounds better to us. Whereas regular noise consists of a combination of random frequencies, not just the fundamental frequency and the integer multiples of that. And so, for example, white noise is a combination of all the frequencies in the audible range, 20 to 20,000 hertz. Similar to how white light is a combination of all the colors of light, white noise is the combination of all the frequencies in the audible range.